Alright, so let's start with section 1.4 talking about right triangle trigonometry. Here, this is going to be very similar to our coordinate geometry where we're talking about points being in quadrant 1 because everything here is going to be positive values. So if you notice, I have two diagrams written on exact same right triangles, but if you notice, the theta is located in different locations. And that's going to affect what we call our SOHCAHTOA rules. This is kind of an acronym for helping you find sine, cosine, and tangent based on the location of theta for your acute angles in your right triangle. So we always want to label our hypotenuse, so I'm going to label the hypotenuse in both diagrams. Now, with reference to theta, theta is an angle A, so opposite side of theta is the side that angle A or our theta angle opens up to. So this is opposite of theta. Then adjacent means right next door. So the side right next door to angle A, or in this case theta, is side B. Now, going over to the second diagram, things are going to switch up here a little bit because we have a different location for our angle theta. It's in angle B. So opposite of theta, now it opens up to side B. So this is the opposite of our angle theta. And now side A is the adjacent to our angle theta. So these will switch around depending upon where your theta is. It's very important to identify theta. So, like I said, my acronym for finding my sine is O opposite over H hypotenuse, all with respect to where the location of theta is. So in my diagram, opposite is A, hypotenuse is C. Cos, C-A-H, cosine will be A adjacent over H hypotenuse. So cosine of theta adjacent over hypotenuse. And in my diagram, that would be B over C. That's my ratio. Tangent, TOA, opposite over adjacent. So the tangent of theta is going to be the side opposite, in this case A, over the adjacent side of theta, which in this case is B. So if I switch the location of my theta, then of course all my ratios are going to switch as well. So here, the sine of theta in my second diagram, now it is opposite over hypotenuse, but now it's B over C. And for my cosine with relationship to theta, again, adjacent over hypotenuse, that would be A over C. My TOA rule, still opposite over adjacent, but that's now going to be B over A. So again, using the SOHCAHTOA rules, you have to find the relationship of the sides with respect to theta, or the angle in which you're looking for. So example 1, let's find sine, cosine, and tangent. We're going to use our SOHCAHTOA rules. What I recommend that you do, again, identify your hypotenuse, identify your angle. You can do these in either order. But once you have your angle, then find the opposite. Draw an arrow pointing to that side, label it as O or OPP, and then draw a little hook curve to your adjacent side. Adjacent means right next door. Label it as A or ADJ, whatever works best for you. Once you have this labeled, now we can find our sine. Opposite, 7 over hypotenuse, 25. That is the sine of angle A. Cosine of angle A, that would be adjacent, 24, over hypotenuse, 25. And our tangent, TOA, opposite over adjacent, the tangent of angle A will be 7 over 24. Example 2. Triangle ABC is a right triangle with C equal to 90 degrees. That is standard practice. When they label a triangle ABC, C is traditionally the 90-degree angle. Here we have if side A is 4 and side C is 5, find the 6 trig functions of angle A. Well, let's go label our sides. A is 4, C is 5. We're going to need to use the Pythagorean theorem to solve for B. So I plug in my values. 4 goes in for A, that's 4 squared plus B squared equals, plug in 5 for C, C squared. Subtract over the 4 squared, or you can make the numbers 25 and 16. 25 minus 16 is 9. The square root of 9 is 3. So the value of B is 3. So all 3 sides are labeled like we did in example 1. Now they want to find the trig functions for angle A. I circle my A or list my sides, my hypotenuse, then circle my angle, or vice versa. You can switch these around. Opposite, A. Side A. Adjacent, side B. Now I can use my SOHCAHTOA rule. Sine of angle A, opposite 4 over 5. Cosine of angle A, CAH, 3 adjacent over hypotenuse 5. Tangent of angle A, opposite over adjacent. So the tangent of A is 4 over 3. There's my first main 3 ratios. Now we'll use our reciprocal identities to find the other 3. So the reciprocal of tangent is cotangent. So we just flip the 4/3 to 3/4. Cosine of A is 3/5. Its reciprocal is secant. And so we flip the fraction. Secant of A is 5/3. And then cosecant is the reciprocal of sine. We'll flip 4/5 to 5/4. And there's my 6 trig ratios. Everybody agree? Now again, if they ask for a different angle, let's say they want to go to angle B. All right, if we want to go to angle B, then now little b is the opposite side. Little a is the adjacent side. The hypotenuse doesn't change. But if we want to find sine of b, that's 3 over 5. Opposite over hypotenuse. Cosine, adjacent over hypotenuse. Cosine of angle B is equal to 4 over 5. Tangent of angle B, opposite over adjacent, 3 over 4. And just like we did earlier, we'll take and now do our reciprocals. The reciprocal of tangent of B is cotangent of B, so you flip the 3/4 to 4/3. Take your cosine of B, its reciprocal is secant of B, flip the 4/5 to 5/4 for secant of B. And the reciprocal of sine B is cosecant of B, so sine of B being 3/5, we'll flip that and make it 5/3. And we're going to take a closer look at all these answers here. Excuse me. Look at angle A and B. First row, second row. Look at those closely, and you're going to notice a pattern. Sine of A, 4/5, is the same as cosine of B, 4/5. Cosine of A, 3/5, is the same as sine of B, 3/5. They're the same. And we can do the same thing with tangent and cotangent. And secant and cosecant, they're the same. Everybody seem to agree. Now, we're going to push this a little further. This is not just by accident because of this particular triangle. This is going to work for all right triangles. So we're going to create a new identity based on these relationships here. All right. So the one thing you should have noticed is that angle A and B are the two acute angles of our triangle, our right triangle. They are complementary. So A plus B has to equal 90 degrees. So we had sine A, cosine A, tangent A, cotangent A, secant A, cosecant A. We said that sine of A was equal to cosine of B. And cosine of A was equal to sine of B. Tangent of A was equal to cotangent of B. Cotangent of A was equal to tangent of B. Secant of A was equal to cosecant of B, and cosecant of A was equal to secant of B. These are called our cofunctions. Sine and cosine are cofunctions because of the prefix CO. All right? Tangent and cotangent, they are also cofunctions. And cosecant, take off the prefix co, and you have secant. These are cofunctions. So what we're creating is what we would say are cofunction identities. Well, usually when you want to work with an identity, if I'm working with angle A, you want your identities to all be in angle A. So here's what we're going to do. We're going to go back up to this relationship. A plus B is equal to 90 degrees. I am going to solve this for B. So I'm going to subtract A over to the 90 degrees. And now that I know what B is, it's 90 minus A. I'm going to come back over here and take out all the B's and replace it with 90 degrees minus A. So this is how we create an identity. Here's sine of A. It's equal to a different trig function using the same angle value. We're just subtracting that angle A from 90 degrees to make them equal. Our two sides are the same. So all these B's, let's take them out. So this B, sine of B becomes sine of 90 degrees minus A. Cotangent of B, cotangent of 90 minus A. Tangent of B, tangent of 90 degrees minus A. Cosecant of B, cosecant of 90 degrees minus A. Secant of B, secant of 90 degrees minus A. So those are my 6 cofunction identities. Just imagine removing this middle column here. All right, so let's practice working with these cofunction identities. All right, just remember, you're going to go from this trig function and put CO in front or take CO off, depending upon what we're given. So cofunction values of complementary angles are always equal. That's what we just showed in the previous slide. So making this work, okay, so it says sine of what angle is equal to cosine of 30 degrees. All right, so I got to take its complementary angle. If I have 30 degrees, 90 minus 30 is 60 degrees. Just remember, whatever angle they give you, subtract it from 90, and that's going to build your cofunction identity. B, here we have secant of 75 degrees. We're going to cosecant. All right, take the existing 75, subtract it from 90. 90 minus 75, 15 degrees. So cosecant of 15 degrees is equal to secant of 75 degrees. C, we have tangent of y. Don't panic. We took the 30 and subtracted it from 90. We took the 75 and we subtracted it from 90. Take the y and subtract it from 90. Tangent and cotangent, this will be 90 minus y. 90 degrees minus y. For part D, I have cosine of 40 degrees, and I need some trig function name with 50 degrees. Oh, look, they are complementary, so drop the co and make it sine. These never work with sine to a tangent or sine to a cotangent. It's sine to cosine or cosine to sine. It's just the removal of the prefix co or adding on the prefix co. All right, let's up the degree of difficulty. Example number 4, find one solution for each equation. Assume all angles involved are acute angles. Cosine of theta plus 4 degrees is equal to sine of 3 theta plus 2 degrees. These are co-functions of each other. Well, if they're co-functions, then my angles have to be complementary. Take the two given angles, add them together, and set it equal to 90 degrees, and we'll solve for theta. So theta plus 3 theta, that's 4 theta. 4 degrees plus 2 degrees, that will be 6 degrees, is equal to 90. Well, we can just drop off the degrees. We'll just go ahead and solve it. So 4 theta, this is just like 4x. Treat it like a variable. Subtract over the 6. 90 minus 6 is 84. We'll divide by 4. Theta is equal to 21 degrees. We should put our degree mark back on there, but apparently I think I forgot to do that. So put your degree back on there. Okay, part B. Tangent, cotangent. All right, cofunctions, complementary. Set those two angles, add them together, set it equal to 90. 2 theta minus 18 degrees plus theta plus 18 degrees equals 90 degrees. Combine, well, wait, minus 18 plus 18, they cancel. 2 theta plus theta, 3 theta equals 90. Divide over the 3. Theta equals 30. Again, I should have probably put my little degree symbol there. I'll go ahead and edit it when we're done, but make sure that you put your degrees there. All right. Now we're going to look at special right triangles. Special right triangles are created from regular polygons. So what a regular polygon is mean that all the sides are the same distance and all the interior angles are the same. So we're going to start with an equilateral triangle. All 3 sides are 2, all 3 interior angles are 60. Well, to make this into a right triangle, you split it down the middle and you cut it in half. So that's going to cut this side at the bottom into 2 1s. And my 60 cuts into 2 30s. And that creates what we call a 30, 60, 90 special right triangle. And here we can now solve for x, this vertical distance, by using the Pythagorean theorem. X squared plus 1 squared equals 2 squared. All right, well, that's x squared plus 1 equals 4. We'll subtract over the 1, make it a 3, and we'll solve for x, and that's the square root of 3. Now remember, you can't have a negative distance, so no plus or minuses here. So this special 30, 60, 90 right triangle has the following relationship. What's ever across from 30 degrees is always a 1. What's always across from 60 degrees is this x, which we found to be the square root of 3, and across from 90 degrees is always the value of 2. All right, now I write this just slightly a little bit different, and I put a's multiplied to every one of those values. The reason for that is the reason you have special right triangles. It's a little bit different than other right triangles. Most right triangles, you have to be given 2 sides to find the third to use the Pythagorean theorem. Here, you only need to be given 1 side, and you can find the other 2, as long as it's a 30, 60, 90 right triangle. So if you imagine that you were given a picture of a 30, 60, 90 right triangle, and they gave you this side is x, this side is y, and this side, let's say, is 4 radical 3. Well, you label this as across from 30 is 1a. 1a equals x. 2a equals y. And your 4 square root of 3 is equal to a square root of 3, which means a is equal to 4. Once you have the value of a being 4, you substitute it into the other two sides. 1 times 4, 2 times 4, you have those other two values of the other two sides. So that's why it's considered a special right triangle. You don't use the Pythagorean theorem. You only need one side to find the other two. All right, so if we had to find what we call now exact answers, sine of 60 degrees using my 30, 60, 90 right triangle. 60 is my angle. Sine opposite, square root of 3, over hypotenuse 2. Square root of 3 over 2. Tangent of 60. Okay, start at 60 again. Opposite over adjacent. Square root of 3 over 1, or the square root of 3. Cosine of 30 degrees. Adjacent over hypotenuse. Here's my 30. Adjacent next door is the square root of 3 over my hypotenuse 2. My next special right triangle comes from a square. So if you could imagine we had a square, all sides are 1, all angles are 90 degrees, we cut it in half, and you make another special right triangle, the 45, 45, 90. Well, if this side is 1, this side is 1, 1 squared plus 1 squared is 2, the square root of 2 is the length of my hypotenuse. All right. Now, so we have this ratio 1, 1, 2. Opposite the 45 is 1s. Opposite the 90 is the square root of 2. But again, I like to put variables in it in case I get some questions where they are giving me one side and I have to find the other two. So what I like to do is to multiply all these values by a letter B. So 1 times B is B, 1 times B is B, and then up here on my hypotenuse, B times the square root of 2. That's the way I like to look at my 45, 45, 90. I also think of this one because, again, if they gave me a picture, this is X, this is Y, and they called this an 8, then I label, hey, my B is 8. Then this is B, 8. Then this is 8 times the square root of 2. Given one side, I can find the other two. So if we had to find all 6 trig functions of the value of 45 degrees, and again, doesn't matter which 45 degree you use. Sine of 45 degrees, opposite over hypotenuse. 1 over the square root of 2, rationalize the denominator, square root of 2 over 2. Well, cosine of 45 degrees should be the same thing because the opposite and adjacent sides are the same. Tangent of 45 degrees, opposite over adjacent, 1 over 1 is 1. So that means its reciprocal, cotangent of 45, is also 1. Secant of 45 degrees, let's flip our first fraction, square root of 2 over 1, which is the square root of 2. And when you find cosecant of 45, the reciprocal of sine, it should be the same as secant. So we'll just steal the same answer, square root of 2. All right. So here's an opportunity. I'm going to let you quickly write down your 45, 45, 90 right triangle. Write down your 30, 60, 90 triangle. And I'm going to give you a second. You can pause the video, find these answers, and then I'll come back and we'll discuss them and give you the answers real quick. So go ahead and pause the video. All right, welcome back. Sine of 45, we said that's going to be the square root of 2 over 2. We just did that earlier. Tangent of 30, opposite over adjacent, 1 over the square root of 3. Rationalize it to the square root of 3 over 3. Secant of 60. Here's how I do this between my ears. I say secant, wait a minute, you are the reciprocal of cosine. So I go to 60 degrees, I do my cosine. Adjacent over hypotenuse, 1/2, and then flip it, 2 over 1, which is 2. Sine of 60, opposite, square root of 3 over hypotenuse 2. Cosine of 30, opposite, check, check, cosine of 30, adjacent, radical 3 over 2. I'm going a little too fast here. Cotangent of 45 degrees, well, that's the reciprocal of tangent. Opposite over adjacent, 1 over 1. Flip it, it's still a 1. All right, example 6. Let's say x is 30 degrees, y is 45 degrees. Let's simplify some of these expressions. So if I put 30 degrees in for x, this becomes 2 times the sine of 30 degrees. Well, if I go to 30 degrees, opposite 1 over hypotenuse 2, that's 1/2. 2 times 1/2 is 1. Sine of 2y, y is 45 degrees. That's going to make it a 90 degrees. Now, if you can't remember that chart that we did, you can still use the 30, 60, 90 right triangle. I'm going to show you a nice little sneaky trick here. Go to 90 degrees. Go opposite 2 over hypotenuse 2. 2 over 2 is 1. 4 times the sine of 3 times x. X is 30 degrees. Well, that'll be 90 minus 90. That's going to be the sine of 0 degrees. Now, again, I can use my 30, 60, 90 triangle. This is how I get sneaky here. I pretend that the 30 degrees is 0. So this drops all the way down to here. So the opposite side is 0 over the hypotenuse of 2. So 0 over 2 is 0, so 4 times 0 is 0. So that's how I get kind of sneaky using my 30, 60, 90 triangles with zeros and 90s. All right, that wraps up 1.4.